try this again. All right. So this is Unit 6. We are covering energy and marrying it with the ideas of electricity and magnetism. We just did it with gravity in the last unit, and now gravity and motion. Now we need to do it with electricity and magnetism. And so the first unit we need to talk about, the first part of it, is electric potential. And to get there, we need to review electric field. Okay. And we need to review potential energy. If I can spell that correctly, potential. Okay. And then we will bring them together with our definition of electric potential. Okay. All right, so if you guys remember, we had our general forces. Remember, we had our gravitational forces were universal gravitational constant times one mass times the second mass divided by the distance between those masses squared. Okay, and technically it would be negative r hat on that because it was always an attractive force. And so if you draw the radius from one object, all right, if that's r, the force would always be attractive in the opposite direction to that vector, and so that's what made it negative. Okay, the gravitational field of that, all right, so the gravitational field, which we didn't really talk about a whole lot. We understand the idea that if you come into the presence of another massive object, you enter its gravitational field, or if you watch any sci-fi, when you get close to a star or another planet, we've entered the gravitational field. Right? All that means is that it's the force of gravity from that object divided by your mass is the field strength at that point. Well, if this is force divided by mass, the force of gravity divided by mass, okay, if you're close to the surface of that object, that's just g. And so close to the surface, that's about 10 meters per second squared, right? So the acceleration due to gravity is the value of the gravitational field around that object. Right? That's really what it boils down to. Okay. So we need to take that analogy, right? And we need to set it to the force of electricity. Remember our electrical force, there isn't any close to the surface exemption for this one. It's pretty much this equation all the time. It's K, which is this electric constant that really equals K equals 1 over 4 pi epsilon naught, and we can discuss that at another time. That's not real important right now. But this K is a combination of these constants over here. K, Q1, which is the charge on one object times the charge on a second object over that same r squared. And this time it's just r hat because r hat means is the direction of the force. We don't have the negative there because we can have positive and negative charges. And if they're both positive, if the charges are both positive or both negative, then it results in a positive force, which means they repel. And if one of them is negative, then they attract, which positive times the negative gives a negative, which means that they're attractive. And that's the math definition behind opposites attract. Okay, but this leads to our electric field. Okay, if we do the same thing, if the gravitational field, if the gravitational field is the force of gravity divided by the thing that's causing the field, right, by the mass of the object, then we do the same thing for electric field, and we take the electrical force and we're going to divide it by the source of by the strength of the source that causes the electric field. And that's going to be the charge on the object in the field. Okay, and this gives us, these are units of newtons per coulomb. Okay. But we really like to write it like this, that the force, electrical force, equals our charge times E, capital E, which is our variable for our electric field. All right, so our force, right, the newtons on our charged object equals the charge on that object times the electric field that it's in. Okay, so really that is just, and I'm going to that is our E, right? So if our force of electricity is KQ and Q2 over R squared, okay, and the force of electricity is the charge on our object, our Q2, times KQ1 over R squared. So E equals KQ over R squared. Okay. So in words, this is, oh, that's too big. Okay, so our real definition is for an electric field is it is the potential energy per unit charged potential energy per unit charge on an object in the presence of another charged object. Right, it's charges and objects and charges and okay. So, what does this really look like? Well, let's go back and review our potential energy. Okay. Our potential energy U, the standard unit for all potential energies, regardless of what kind, is really this. So if we have some ground level, and we have an object here, and we move it here, what we've done to measure that potential energy, okay, this U equals the force it took to move it there times the distance. So in other words, it's just the work that it took to elevate it away from one position to another. All right, work equals force times distance. If we're doing work in a gravitational field, that work, it becomes the potential energy, because if we were to release that object, it would fall back down and that would all become kinetic energy again, right? Okay. But is there a difference between moving it from there and moving it here? Okay. Is it more potential energy if we move it over there? No, the height stays the same, right? It's all based on this distance. Okay, or that delta r. Okay. These two don't matter. Okay. This same principle applies if you have, say, a planet, and you have an object orbiting the planet. There is right, our potential energy here is, well, we didn't get into gravitational potential energy, but there is a gravitational value here. And then if we move further away, we'll call this U naught, and we're getting all right. So if we have an object that has a potential energy of U naught there, and it moves to this other position, let's say it's a little further away from the planet, there, okay, it doesn't matter how it got there. The only thing that matters is that R naught and R1. Okay. The only thing that matters is that it got further away from the planet, right? It doesn't matter that it's further to the left or to the right. It's only a radial change. Okay. And so this is path independent. And so what we have here is what we're really concerned about is our change in potential, which equals U1 minus U naught, U final minus U initial. That's it. That's our change in potential energy. Okay. Are we good so far? Okay, that the only thing that mattered is the difference between R1 and R naught, okay, for our potential. Now, there are other factors at play, because as you move further away, then you also have a decrease in the force on it. And so there's some calculus involved here, and I'm glossing over that because this is not a calculus class. But the idea is that it doesn't matter how we get from here to here, that there is a change in potential, and it's primarily involved with the change in the radius of the change in the distance from the center of the planet. Okay. Okay, and how this is similar to this. Can you guys extrapolate that if it's close to the surface versus further away from the surface, doesn't really matter except the amount of force changes. Okay, but that isn't affected by how you get from one point to another. Okay, so that brings us to electric potential. Okay, and this is based on the very similar thing, that our potential energy of our electricity, okay, equals, okay, still equals our force times our change in distance. Right, so it still equals the force times the distance, the change in distance from our other charged object, the field that it exists in. Okay, but remember, our force is Q times E for our electric field. Right? It's the charge of our object times the field that it's in times our change in distance in the field. All right, so that kind of looks like this. So we have a charged particle here, and we've got another charged particle over here, and say this is a positive charge, and this is also a positive charge. Okay, if we move that charged particle away, then we still have the all right, so we have our first radius and our second radius, and we still have this R0 and R1. And so our delta R is still R1 minus R0, or our initial position minus our final position. If we have a displacement. Okay. The only thing that matters, though, is how far away from our charge it is. Okay, so once again, delta U is path it doesn't matter how it gets from one place to the other. Okay, it just matters the distance from the source of the charge. Okay. Now, this will change, just as in a gravitational field, the force will change if our mass increases. This will change if our charge increases. And so we have this unit of delta U per unit charge. This is our electric potential. Okay. It is given by the variable V. Okay, our electric potential is given by the variable V. It is the change in potential energy per unit charge. Okay, it equals a joule, because that's our unit of potential energy, per coulomb, which is our unit of charge. And this joule per coulomb is called a volt. And I'm sure you've heard of volts before. Okay, most of your batteries that you plug into things, okay, if they're not rechargeable, or even if they are rechargeable, okay, they are 1.5 volts. A AA battery, AA, AAA, D batteries, the big fat ones, they're all 1.5 volts. And they just hold different amounts of charge, different amounts of energy in them to be delivered at the same voltage. Okay, so that is the idea behind electric potential. I've also published the electric potential text to you in Google Classroom, and I believe the assignment kicked out too. Yes, and there's a problem set. So that is what you guys are up to now, and good luck.